Okay, and this next slide looks at a city around the concept of traditional stormwater management or watershed management. So the green blob in the middle with these segmented areas, which are sub-catchments in your watershed, is a city, suppose. So you've got A through to H of areas of watersheds within the city. The traditional approach is managing your wastewater and stormwater flows down at D, down at the bottom. But throughout the city, there's stormwater's running through the system into your stormwater or wastewater collection system, depending on what you have. And if we look over to the left in this picture, you've got the allotment, which is a property. That's the stormwater that's running off that. It's known as a hydrograph. That's the shape of it. Then a little bit further down the catchment, you've got two properties coming in together. So you've got the two patterns of stormwater runoff are coming together. And as you get down to the sub-catchment, you've got a bigger hydrograph, as the engineers call it.
Is that just volume over time? Is that what that is on that the Y and X axis?
Yes, it's actually volume over time.
Yeah. Okay.
And the very peak of that axis is peak flow, which is often used by the stormwater engineers. So right down the bottom, we call a catchment. You guys will call a watershed. You can see it's a very steep volume over time graph or a hydrograph. So that's traditional. And if you have a combined sewer system, that's adding to the risk of overflows of your sewer system. It's adding substantially to the treatment costs of your...
Yeah, and just to, if there's any of our students who aren't familiar with that, it's how common is it that municipalities or cities actually combine their storm sewer with their sewage treatment? Because that just seems rather...
Well, in Australia, Michelle, the city of Sydney got rid of their combined sewers in the 1800s and separated stormwater from sewage treatment and greatly reduced the risk of sewage overflow and treatment plant costs and so on by doing that. There are arguments in places in Europe and North America of no, it's more efficient to combine them together. I would probably strongly disagree with that, but we could come back to that later in the course. If we go further about this city, you can see, say California, for example, we're actually taking water from a river and a water supply catchment that's a long way away from the city. The city takes water from someone else's catchment. It transfers the water a long way to have water supply to that city. And it might also need desalination or other sources of water to supplement that supply. Downstream of that dam in someone else's catchment to supply the city or a different region, with dramatic changes in the viability of the river or the waterway that's providing those resources. It could even be a groundwater source. And it's actually changing the availability of water to downstream environment. So this is a systems effect. So, which I'll talk about in the next slide, but imagine if all the management wasn't down the bottom at D and all the water didn't come from someone else's water supply catchment in A. Imagine, or from desalination, what would happen? So we get this, and to understand this, we have to understand what we're actually working with is a linked and non-linear system. So everything's linked, its behaviours are non-linear. So if we go back to our city concept here, just say in the sub-catchment, so part of the city, watershed G in the city, what's really going on in there? There's a whole bunch of things that city planners and others are trying to do in the modern era. So you can see there's greens and yellows and different colours in there. It's because there could be local management of stormwater flows by using vegetation, soil profiles, rainwater harvesting, but there could also be local management by good town planning decisions, like putting parks and gardens in there and street trees to change heat island effects, stopping fighting nature and working with the topography and the local conditions to actually slow down stormwater leaving that system, which actually will change the cumulative effects. So if we look now back to the allotment, remember on the previous slide we had the red volume versus time graph, as Michelle pointed out, which the engineers called hydrographs. We can see now if we're taking some of the volume of water out at the property scale, at the home scale, you could have the effect of some of the rainwater is now kept on site, and the blue bit is what's left. So that's what's known as a sawtooth hydrograph. So the volume is taken out of it. So if we go downstream one property, we can actually see that these two partial hydrographs are entering the system because both of them have got volumes missing, and we've deliberately shown it in this way because in these cases the peak flow doesn't change but the volume changes. So the peak flow at one property doesn't change. This is important for engineers who assume that process dominates throughout a catchment. It actually doesn't. So we get down to the sub-catchment scale, and what you're seeing now is the blue volume time graph is quite different to the original red one. It's got a different volume, a lesser volume, and an increased timing of flows. That's because the volumes have been taken out from rainwater harvesting or permaculture or vegetation or whatever the city planners are doing. And you can see right down the bottom, the catchment, or as in North America you might call it the watershed effect, is completely different flow characteristics. This is actually very important because when you use traditional engineering analysis, you can't see this systems effect, and you don't actually see there's actually a benefit. But when you actually use systems analysis to account for the real system, changing volumes in the catchment, which you're doing with rainwater harvesting and other home scales, property scale solutions, you're actually dramatically changing the volume of flows in the stormwater system and the timing of those flows.
And it's not a simple volume times number of, or the average volume times the number of households.
In fact, it absolutely isn't. And thanks for asking that, Michelle. We just won the Alexander Medal in Australia for proving that is the case. Very controversial, but the best scientists in Australia reviewed our work, and we won this medal for science, for actually finally proving after 20 years that the engineering assumption here is actually not correct. So there is quite a benefit. This is what's known as a cumulative response from the bottom up. So what do we mean by bottom up? It's driven from the property scale of reducing the volume of water running off from rainfall at the property scale, and it adds up through the catchment to produce, which is cumulative, to produce quite a beneficial effect. There's another thing going on here that's quite important. So obviously you're taking less water out of the dam in someone else's catchment. So your dam is more resilient over time, which we'll talk about in a different lesson. So downstream of that dam, you're allowing more water into that river because you're not taking as much. So you're improving the environmental health of that waterway, and you're allowing more water to be available in that system two other settlements that are further downstream. As that river, if it does indeed, passes that city or that region, because your stormwater runoff is reduced as well and your water quality problems are reduced, you're changing the water quality of that regional waterway. And remember, you've got better environmental flow characteristics of that waterway because you're taking less water out of it. So you're overall massively improving the health of that and the resilience of that local waterway. That's a systems effect.
Mm-hmm.
So those who are into city planning, and we're not saying rainwater harvesting will only be in cities, but there's a few issues about what we call cumulative transport issues, transport logistics, say in water and sewage services. The bottom graph is for the city of Melbourne in Australia, and apologies for the Southern Hemisphere example, but hopefully we'll do some in the US one of these days. The darker the colour is the further the sewage is transferred from properties to the nearest sewage treatment plant. So some of those transfer distances are over 60 kilometres. And as we can see underneath the graph of the sewage pathway, and it's not all downhill. In the case from the most dense area, which is the furthest transfer distance because it's the inner city area, to the sewage treatment plant, it's actually transferring by very large pumps the sewage uphill and then downhill to the outflow. If you were just examining the sea level at the outflow from the sewage treatment plant and the level of that inner city location, city of Melbourne in this case, you'd think, oh, it's downhill there, it's no problem. But if you examine the pathway of the infrastructure, it's actually uphill a long way, I think 200 metres there, before it goes downhill. There is actually some of the biggest pumps in Australia in that system. If we take it to the blue map in the top corner, that's the water transfer distances from the nearest water supply reservoir around the greater Melbourne region. So the darkest colour is almost black. It's over 100 kilometres transfer from the dams. And again, it's not all downhill from the, as you see in the water pathway graph, it's not all downhill in the major infrastructure pathways. The reservoirs are typically up in the hills. However, the pathway and the infrastructure, in this case to the inner city of Melbourne again, is up and down hills all the way to Melbourne. And in this city, which has about 5+ million people now, there's 375 large water pumps, not local water pumps, in the system. This is important because systems concepts also mean talking about transport. So if you're into sustainability, you would hear often about food miles. There's also, in traditional water management, there's the concept we should be talking about, which I'd call water and sewage miles. And as you can see here, this works in 3 dimensions. It's in 2 dimensions where transferring in a traditional water supply and sewage management approach, we're transferring water and sewage a long way across the city, but in the vertical plane, we're also lifting water and sewage up and down hills to get it from the source to the user on a property, and to dispose of most of it from the user of the property back to the ocean to a sink. So systems are about from source to sink, and what goes on in the middle, which is often not counted, is a fair bit of transferring water and sewage miles. So say in the middle of the brown area, so close to the inner city of Melbourne for the sewage, and which is sort of almost dark blue in the water supply area, if you halve the water use in your house because you're rainwater harvesting, for example, say, you would dramatically change the transfer of water to that area and the disposal of water as sewage away from that area, you're dramatically changing your water and sewage miles.
Just Peter, before you leave that slide, I'm curious: is that these, I want to say embodied energy, but it's both, like you said, embodied energy and kind of a continual energy use. Do any cities, do any municipalities that you know of actually have an understanding? And you'd think you'd be able to actually calculate what that number is. Shouldn't be that complicated.
Well, it shouldn't be that complicated, but classical engineering is taught in an average deterministic manner.
Mm-hmm.
So we don't actually train our water engineers at universities, and I am a university professor, about the system they're working in. It's only in the new age we've started to do that. But the traditional textbooks about water management and wastewater management are still very average, not systems focused in their approach. It's a really good question, Michelle, because apart from the work we've done in Australia on these systems, and we're doing some work now at Anglian Water in the UK, Bob Wilkinson from University of California started doing work on the energy water nexus, but it was very much average top-down nexus work. He worked with me on one of these studies in Australia, and he kept telling me I needed to come to North America and do some cities to show them. He was concerned that these numbers would be quite large for cities like LA, for example, and Vancouver. So, and I suspect they are. Unfortunately, all this work is not being done yet. I hope it will be. So if I can talk to this slide, which actually is a good segue to your question, Michelle, because the policymakers who make these decisions about what works and what don't work, and I've worked in the policy advice domain for 25 years, are very concerned about, yes, we could trust rainwater harvesting and permaculture and all these local things we can do, but it's not managed by a utility, so we're uncertain about whether it's going to work and whether we can rely on it. So, look, we just won't count it. We don't think it works. But that's actually not entirely correct. So if you look at this slide, the circles where A is talking about economics, B is talking about environment, C is talking about water resources. And where those circles overlap, and as I've coloured it in blue, is when the policymakers are deciding what works and what doesn't work for watershed management and water supply and so on. Where those areas overlap, they're fairly certain and say, okay, we're certain about that. And it's normally a fairly traditional solution. And in that process, when they're uncertain, which doesn't mean the idea doesn't work, they tend to discount the other things they don't know a lot about, say rainwater harvesting, as being uncertain, therefore it's not in that space where they're going to make policy. Excuse me. So if you go to the big diagram where there's a large area coloured in, what we've actually found out that if you actually do things locally rather than centralised, the uncertainties about performance actually cancel out. And let me give you an example, and this is classic.
Good, because I was going to ask for one.
So classic systems thinking, Michelle. So if you're relying on one water treatment plant to supply 1 million people, and say it gets contaminated, you could make 1 million people sick. Or say it fails for some reason, you can not supply water to 1 million people. So you have a catastrophic whole of systems effect. If in that system you also have a million rainwater harvesting systems, they're not all going to fail, are they? And if one of them fails, it doesn't affect the others. So the uncertainty about one source of water is overwhelmed by the fact that you have a million sources of water, so they're all not going to fail. Right. Whereas if you've got a water treatment plant supplying the whole city, if that fails, you're in trouble. So they're very, very different concepts. So quite the opposite to the thinking that goes on in traditional water and sustainability industries. The very big plant has the most risk. A city that has multiple water sources at multiple scales, particularly local scales, is far more resilient, which we'll talk about in the next course, and its uncertainties are diminished because they're all the water sources aren't going to fail together. So.